All right. All right. Thank you, Mark and Ruben, and thank you for the introduction, and thank you for all for being here and listening to us ramble on about shape spaces now for the next 90 minutes. I should start my timer. And yeah, so what is shape spaces? So, or maybe a word about us before we start talking about shape spaces. So I'm Josua Sassen. I used to be a postdoc at the ENS Paris-Saclay. Right now I'm sort of in between jobs. And this is Florine Hartwig. She's currently still a PhD student, a senior PhD student at the University of Bonn. And we've worked together on these topics for quite some while now. And I will try to give you our perspective on what this is. This is a huge topic. 90 minutes, you could do like a whole lecture course on this and still not be finished. There's like whole books on this. So we try to give you our glimpse of this topic. So I guess the first the first question that you can have is when you talk about shape spaces, what is a shape? Because shape is sort of a thing that you might have an intuition for, but you also need to sort of get to something more formal to actually start to do math, start to do computer science to work with this. But for the beginning, we will stay with a very informal definition which is by David Kendall from the 80s, which is saying that shape is what is left when the effects associated with translation, scaling, and rotation are filtered away. So basically you're saying, okay, shape is really just something intrinsic of an object, or intrinsic is also a hard word, but it's still something like the geometry of an object modulo its position, orientation, and size. Because if you think about graphics, that's just like rotating your camera or zooming or whatever. So it's not really changing the object, just how you look at it from a rendering point or something. So what you see here is all these kind of things. Well, why isn't the other one moving? Yeah, whatever. So these ones, you see this the same hand, it's the same triangle mesh, it's just like moving. The other ones should be rotating and scaling, but they don't. But you can imagine what should happen, and there's all the same shape still, right? Intuitively, you would say it's the same thing. But we will talk more about what actually shape is, like some different definitions that you could use, because you can see there's different ones, and we'll work with different ones along the way. So what is a shape space? So it's something like saying, okay, take all possible shapes they can have. Let's take all realizations or triangle meshes or all like the surfaces in 3D, and we say, but module rigid body motions, right? Because I've said before, like orientation and position and scaling doesn't matter. Scaling is a bit of a thing that depends a bit on your application if you consider scaling or not. Because, for example, if you think about a tumor and you want to model the shape of a tumor, size very much does matter. So, depending on this, but rigid body motions usually say that's fine. So basically, okay, you have a set, you have some and then you want to do things on this set. So basically, okay, you can imagine I have a space, I have something, we will define this closer, what the space is along the way, and each point in the space is a shape. And really, it's a different shape in the sense that, for example, the hand has like different positions of my hand. And then I want to put relations between these shapes, right? So we want to be able to compare shapes and say, okay, these two shapes are more or less the same. These shapes are far. And then we want to build on top of this different operations. We want to be able to do statistics on shapes. We want to interpolate, extrapolate, and so on. Why do we care about shape spaces? So because they have like a lot of applications in different fields. I think the most classical applications in computer vision, or was used, it's not so popular anymore now after all the deep learning revolution and whatever, but it was used basically as a shape prior, and it's like scene understanding and so on, and saying, okay, I know in the scene there should be, let's say, a hand somewhere, so I have a model for a hand, and then I can try to fit this model to my scene and try to find the hand and the position of the hand. Then in computer graphics, which I think closest to home in this conference, you can use it to model characters or whatever and create models for shapes, and then you try to have like a reduced model of plausible shapes, for example. And so this is basically also where we mostly come from in our things, and there'll be a bit of a focus throughout the talk. And then one application that I think is also like very exciting is like medical image analysis. As I just said, you can like look at the shape of a tumor, for example. Or classically, you could look at the shape of brains, or for example, if this book you see here by Xavier Pernek, you see this is the shape of a hippocampus in the brain, and the shape of it is like very important to understand like the progression of Alzheimer and so on. So this is like another field, but this is like hugely popular. And the thing is, all these different fields have different applications, right? So for example, computer graphics, we care a lot about like something should be real time or should be fast, should be easy to use. Whereas in medical image analysis, that's maybe not so important. It needs to be reasonable fast. But the problem in medical image analysis is the heterogeneity of data, right? So you have like MRI scans from different MRI scanners, the quality is not great, the data is not pre-processed nice, and so on. So you have to have different aspects of your tools to work with this kind of data. So the roadmap for today will be, okay, I'll continue a bit on the introduction of this topic. Then Florine will take over and we'll talk about the mathematical framework that you need to understand this topic. Then I'll take over again, jump back and talk about computational framework, like how to get from like some theory to like more like algorithms in the end. Then we talk a bit about like software frameworks that are out there. If you want to work with this topic, what kind of software, what kind of frameworks could you use? Then we talk a bit about some recent advances, which is basically a bit of shameless advertising for our work. And then we move to like open problems. So basically that in the end, if you think this is a fantastic topic, I want to work on this, you may have some starting points that we think are interesting. I think there are many more that you could work on. But this is sort of the roadmap today. We've tried to give you like a broad picture, like a broad view of this topic. As I said, we cannot go into depth too much in everything, but we give you like pointers where you can look if you want to learn more about this. So to continue or finish off the introduction, let's get a bit more concrete what would be a shape, right? So there's different like shape representations that you can actually use mostly if you talk about like implementing stuff in a computer. So the one thing is, we look at a shape and we said it's this thing we look at, and typically, okay, and this first thing would be like boundary models, like triangle meshes, Eurographics, but we do a lot, which we call discrete surfaces or surfaces. Really, so then you represent your shape as a surface in 3D. Or more D, but typically 3D. Or you could also just look at discrete curves. For example, here you have like the, I think this is some cell nucleus, and then you have basically the border of this and look at the shape, or you have this tiny snake. If you want to play like a 3D snake video game, then you could use this. Then what you'll also see more of this, during this conference is this picture, maybe like on Thursday, I think. But this is basically about representing your boundary of your object using an SDF, like assigned distance functions, which has been exactly popular like recently through all neural SDF work. Again, has been popular before and now it is popular again. Then you can do a bit more if you, for example, care about not just how your object looks from the outside, but also how it behaves on the inside. Then you can look at like volumetric models of your object, if you compare composition and so on. So you could look at tetrahedral meshes or hexahedral meshes and so on. Yeah, this is admittedly, it's not something I've never really worked on, so it's a bit foreign to me. I understand it, but it's not so common in the shape space world actually, because we will see that shape space already are quite expensive. So like choosing a like low dimensional representation might help you. So like rather surfaces than volumes. Then another like world of things looks at shapes not through like their own shape, but through how they are deformed. Like they look at deformations, diffeomorphisms, that warp space. And then sort of the object is warped with this deformation. And for example, here's like the very classical things. If you took like people from Paris that work on shape spaces, they will always show you this picture. And it's a book from the 1970s about like shapes of objects in like nature and saying that you can relate shapes of fishes, for example, by looking, by just stretching like this grid that surrounds it. And then you can sort of put relations between fishes and how they, how they put together. And the same for like the shapes of skulls of different monkeys, humans, and so on. And this has been used a lot in like this medical image analysis field I've been talking about. So here you see it applied to an MRI scan to sort of match different brains and to put relations between them and say, okay, is this shape maybe abnormal or not, and so on. So this is where this has been hugely popular. But if you can talk about images, so image somehow is also like a shape for us, which is a bit weird because it's sort of just a rendering of a shape actually, but still like something that happens a lot in real life, right? You take a picture of something and you want to put relations between pictures like MRI scans and so on, but really we could care about the shapes that you see in this picture somehow. So instead of like looking at transformation of images, you can also directly like work with images and derive some like notions on images themselves. And then one final thing is like landmarks. It's like a very simple representation. It's basically just a point cloud. And for example, here it's applied to like a jawbone. And for example, in medical things is used because it may be easy to annotate and maybe easy to put relations between to say, okay, this certain landmark is at a certain point on a certain part of the body and so on. And it's also, again, like very low dimensional. But yeah, you could also do this with huge point clouds, which is sort of like the landmarks. So what are typical goals I want to do if we talk about shape spaces? The first thing is you want to talk about interpolation between objects. So this basically what you'll see for certain reasons, this is like the base problem. You want to have two shapes and you want to compute a interpolating path between them, which is natural in some way. What natural means will Florine tell you in a second in a mathematical framework. And for example, here you have these two tori, or like elliptical tori, and then you go from one to the other by sort of pushing through the middle and like deforming and warping it. And this should be like a natural smooth deformation. Then another thing is like extrapolation. So you start with two shapes. So the first two ones are given. And then you want to see, okay, how does this series of shapes continue in time? Like a natural continuation. For example, here you start with a very slight movement of the arms, and then you get this sort of flossing movement. If you want to build your flossing dance for Fortnite, then this would be like the first thing you can do. But then you want to do more interesting things. You want really to process collection of shapes, right? For example, will be the average shape. So what's the average shape of a kidney, for example, in a human being, and sort of what are variations of this? And so this is, for example, these examples down here, or what's the average shape of a vase in your vase collection, for example. And then you basically want to do this. What you can also do is sort of deformation transfer. So you have basically interpolation as we've seen down here. You have this cat that starts moving, and then we have a tiger. And so you want to transfer this moving operation from the cat to the tiger by putting relations between all these kind of things in our shape space, and then being able to transfer this. And with all of this, I see a bunch of things that you want to do, but the question is, how do we do them? And so as I said, the roadmap, the first we learn about the math that goes into this a bit. And once we have the math, somewhat set, and a lot of this will be somewhat familiar, just a bit different, we can talk about how to put this into computations afterwards. But for the math, I will hand over to Florine.
Okay, so I will start giving you a way to model this in a mathematical language. And the first observation that you might want to take is that actually these shape spaces are not vector spaces. And this you see if you take, for example, these two human shapes, and then you could think about, okay, I want to compute some shape in between, and I just take the Euclidean average. And then you get something like this, which is most probably not what you would like to have, but instead maybe like a pose like this, which really gives you a meaningful in-between pose of these two shapes. And a similar thing you can observe in the space of images. So here again, if you just take some Euclidean midpoint between the two shapes, then you get some image, but it's definitely not what you would like because you have some strange overlay of features, but maybe it should look something like this. So in order to deal with such spaces that are not vector spaces, so they are not linear, you need some additional tools. And the idea is to use tools from differential geometry. And maybe you are more used to this on surfaces in R3. So if you look at this torus, then also there, if you have these two red dots given and you would like to interpolate between the dots, you are not getting a straight line, but you get a curve on your torus. Because also there, if you would just take an Euclidean midpoint, you wouldn't even be on the torus, but somewhere in the middle where you definitely don't want. And this interpolation on the torus refers to a geodesic curve. And you can also extrapolate on the surface. So there you start at a point and you have a tangential direction given, and then you start moving in this direction, and what you get is kind of a loop that wraps around your torus here. And this refers to what is called the exponential map. And so the deformation transfer is a bit more abstract in the setting, but basically what you want to do is you have a curve on your manifold, you have a direction, so this is the black arrow, and then you want to find a way to meaningful transport it around the curve. And this is what is called parallel transport. And the notions below actually come from interpreting the torus as a Riemannian manifold. And doing this then gives you access to those tools that give you a mathematical framework to meaningfully compute all this stuff. So the goal, what we want to do now, is seeing the shape space as a Riemannian manifold, because then we can actually use all those tools and transfer them to the shape space setting. So the general idea is that you pick a class of objects. In this case, they are all circular shapes. So you start with some object, which is in this case the closed curve. And then you can think of different realization of this closed curves, which, for example, this P, Q, and R shapes. And then the shape space would consist of all those collection of closed curves. So a point in the space M corresponds to one of the closed curves. And now to measure stuff on this manifold, you need some way to measure how expensive would it be to deform your object. So for example, here you start in a point P, which refers to this ellipse circle, and then you want to have a cost that tells you how expensive would it be if I now go in direction of this arrow U and get a sequence of shapes. Or how expensive would it be to go into direction of V. And what you can already see here is that most probably you would like that going in direction of U is more expensive, because in this direction you see that you get more complicated deformations, whereas the deformation in direction of V is kind of a smooth path. So another example that you can have in mind during this section is a space of immersions. In this case, you have human shapes, and you have your manifold where each point corresponds to a human shape. And then again, the shape space are all possible configurations of the shape, but without the rigid body motions. And if you prefer to think about discrete surfaces, then you can think of discrete meshes, and you fix a mesh topology, and then you can represent each shape just by the vertex coordinates. So now the question is how to model this mathematically. So we want to have a Riemannian manifold. So the first thing that you have there is a tangent space. So you have a point that corresponds in this case to this hand model. And then attached to this, you have a linear space, which is the tangent space. And in this tangent space, vectors actually correspond now to small, so infinitesimal deformations of your hand model. I hope you can see this figure, which somehow should indicate that if you now move in direction of U and V, you get like infinitesimal deformations of your shape. And the Riemannian metric then defines a metric, so a scalar product, exactly on this tangent space. So it tells you now, if you move in a direction in this specific tangent space, how costly should this be? And the important thing is here that this metric depends on where you are in the space. So if you would be at another point Q with a different hand pose, then also this metric would look differently. But this now allows you to actually measure the length of a path on your manifold. So now gamma is a curve that connects P and Q. So it's actually kind of a deformation path between the two hand poses. And then you can measure the path length, just measuring the usual length of a curve, where you have the Riemannian metric in between. And now, because gamma is a deformation path between P and Q, the time derivative of this path actually corresponds to a shape variation. And the metric tells you how expensive would this be. So this allows you then to define a distance between those two hand shapes by just taking the path that minimizes the length. So the distance is the minimal length between of any path that connects 2 points. So it basically tells you if you have a meaningful metric, then two shapes are close to each other if you have a deformation that has a low cost. So it's probably a small deformation. And instead of looking at the path length, you can also consider the path energy, which looks similar, but without the square root. And the second line is just a rewriting to maybe, so there you can maybe relate it to some kinetic energy. So you see that you have the squared norm of the velocity of your path, but measured in this Riemannian metric. And then you can define geodesics as minimizers of this path energy. So the geodesic, or the meaningful interpolation in this case, would be the path that minimizes the energy, so has the lowest energy. And what you can actually see is that if you now compare the energy and the length of a path, then actually if you square the length, you can just apply Cauchy-Schwarz inequality and see that it's upper bounded by the energy of the path. And Cauchy-Schwarz also tells you that the equality holds if the velocity is constant, so if this norm part is constant. And this relation now tells you that if you have a minimizer of the energy, it's actually also locally length minimizing, and it has constant speed. And this kind of also makes sense if you think about, okay, I want to have a geodesic as an interpolation, then it makes sense that it should also be locally length minimizing. So now the question is, what does it mean to have constant speed? So normally you would say, okay, if I have a curve somewhere on a manifold or in space, then constant speed means you have no acceleration, so the second derivative is 0. So here you have to be a bit careful because this norm is really measured in this Riemannian metric. So we will examine a bit more what this means in case of geodesics. And for this, we will shortly leave the shape space context, and just to have a bit simpler setup, we now consider just a surface in R3. And now a minimizer of the energy, so this holds in general, solve the Euler-Lagrange equation. So if you're not familiar with this, it's similar to if you want to find the minimum of a function, then you set the gradient to 0. And now you have a minimizer of the energy, and you basically do a similar thing. You know that it should fulfill this equality where you set the first variation of the energy to 0. And for this, we will simplify even further and just consider Rn, or you can think of R2. So there now the path energy simplifies a lot because you can just take the Euclidean metric. And now to formulate this Euler-Lagrange equation in this setting, you compute the first variation. So the first line is basically just writing out what it means. So what you do is you compute the derivative in direction of a small perturbation. So this is this nu. And then you take the derivative at epsilon equals to 0. So this happens from the first to the second line. And in the third line, it's just integration by parts. And now you know that because a geodesic or minimizer of the energy has to solve this equation, it also has to solve it for any function nu in which direction you compute the minimizer. So you get this, this equation, and now this has to hold, if you have the minimizer, this has to hold for any nu that you put inside. So what comes out is that to fulfill this equation, actually already the second derivative has to be 0. Which refers to having a straight line. And this is probably something that you would have be able to say without doing any calculations. So the interpolation between those 2 points should be a straight line. So now if we would move to a hypersurface, so a curved manifold, then this can't be true any longer because a straight line wouldn't be on this manifold. So there has to be something else. And what actually comes out is that in this case, your second derivative is not vanishing completely, but it's vanishing in tangential directions, which you can also see from the variational formula, if you like. So there you now compute the variation only in direction of your manifold. So the nus that you put inside are actually only tangential directions. So this means that on this hypersurface, you only have acceleration in normal direction. And this is what you can think of as having a path that is as straight as possible, but on a curved surface. So there it can't be a linear path, but it's as straight as possible. So we already saw that having this constant speed has different meanings in a way if you are on a flat space or a curved space. So the question is, what is like a general notion for this? And for this, we need one additional concept, which is the covariant derivative. And we will also look at this only in this hypersurface setting. So what you actually want to do is to measure this change of the velocity. You normally would compute the second derivative. So if we do this here in this hypersurface setting, where so we have a surface in R2, and a two-dimensional surface in R3, and we have this vector field WT. And what we could do is just computing the usual time derivative. So this is this W dot. And now this time derivative, because we computed in R3, has a component which lives on the surface, and it has a component that maps away from the surface in tangential direction. And now if you want to define a derivative on your hypersurface, then you only can care about the tangential part, because the other part isn't even belonging to your surface. So on this hypersurface, the covariant derivative along your path is just the projection of the derivative on the tangential component. So if we apply this now to the time derivative of our gamma dot, then it's actually the tangential projection of the second derivative. And now this allows you to actually reformulate what we've seen before. So we saw that geodesics as minimizers of the path energy on a hypersurface fulfill this property that the acceleration vanishes in tangential direction. And now the second line is just rewriting exactly this condition in terms of the covariant derivative. So saying, okay, for a geodesic, this term has to vanish. And now we can formulate an initial value problem. So now we are not computing a geodesic as an interpolation between 2 points P and Q, but we start at a point P and we have a velocity W, and now we want to find a geodesic in this direction. So what we do is we can solve this problem, and actually the result gives us a geodesic, because a path that fulfills this equality fulfills this property that we've seen that a geodesic should have. So we can now not only compute geodesics between 2 points, but we can use them to extrapolate in a direction. And just to give you a short idea how you would do this in the general case. So this is basically the same setting. And I just want to mention here, you can compute again the variation of the energy. And it gets a bit more complicated, and this is because now your metric depends on where you are in space. So actually, there are now another terms appearing that you don't really have to care about, but you can think of, okay, now, because we are computing derivatives and the metric depends on where you are in space, you get additional terms that come from this dependence. And again, if you do integration by parts, you see a second derivative, and then you see these green terms, which are just coming from this relation. However, there's actually a way to formulate the covariant derivative also in this setting, and it just is somehow the second derivative, but correcting for the additional green terms that you have seen before. So it gives you a way to compute a second derivative, but making up for the curvature of your space. And the important thing is it gives you really a direction that lives in the tangent space, so in your manifold. And there's a way to define this without ever considering an embedding space. So this then allows you to, just to summarize this allows you to formulate the initial value problem also in the shape space context. So you basically, you start at a point, you have an initial velocity, and you solve this ODE, where it is a second order ODE because of the second derivative, but it's a bit hidden because it's just hidden in this symbol. And then the exponential map is defined as the endpoint, so the endpoint of the solution of this geodesic ODE. And you can also consider now the logarithm. So this answers a different question. So maybe you have point P and point Q, and you want to know, okay, I'm now in point P. In which direction do I have to go to actually arrive at point Q? So this is defined as the inverse of the exponential map, and it tells you, given 2 points, what direction do I need to take to connect them? So this was maybe many math terms, but just to recap the most fundamental things here. So we have a Riemannian manifold, which is the shape space, and every point corresponds to a shape. And we have a metric on this space, which describes the deformation costs. Then geodesics are a way to interpolate, and they are defined as minimizers of the path energy. And just reformulating and using a property of the geodesic, we can also reformulate this in an initial value problem, where now you start at P, you have a direction W, and you want to compute in where you end. And the logarithm gives you a way to find a direction that brings you from P to Q. So, of course, there are many introductions to Riemannian geometry. So the first 2 lines here are basic introductions. The third one is the book that we have seen before, which already has in the first chapter also an introduction to Riemannian geometry, and already in the context of the shape spaces. So this might be a good start if you're interested in this. And because all of this was a little bit abstract, we will have a look at examples that hopefully make these concepts clear.
All right. We forgot about this in our roadmap. We've been lying to you a bit. I just realized. Okay, so for example, I want to talk about is the space of discrete shells. It's basically the thing that we've been seeing now for the whole time as example, like these like three-dimensional surfaces that you've been looking at. And this is basically the space to do this in practice. So what's a discrete surface? For us, a discrete surface is just a triangle mesh that is nice enough, so its topology is good, let's say. And then we look at, as we said before, okay, we have in the shape spaces, we have some object, and then we look at realizations of these objects. And in this case, the realizations we look at are piecewise affine immersions of our triangle mesh into R3. Or if you want to be less fancy in your terms, just say, okay, I look at my nodal positions of my triangle mesh, how are they placed in three-dimensional space? And what you want is that you don't want your triangles to degenerate, so they don't collapse, and you also don't want to collapse neighborhoods of like one vertex. So it should be somewhat decent, let's say. And then, okay, the space of discrete surfaces, as I said, is just at first the space of all of these immersions that you could have. But actually, life is a bit more complicated because we talked about in the beginning that sort of we say if a shape doesn't, if you don't change, like if it's rotated, you translate it, so you have rigid body motions, it doesn't change the shape. So basically something like this, okay, I care about my immersions modulo SE3, so rigid body motion, saying, okay, two things are the same if there is a rigid body motion that puts them onto another, which makes everything a lot more complicated. We will talk a bit about how to deal with this in practice. And mostly you just ignore it. That's the most basic trick you can do. But that's sort of the space that you think about that we want to work on. And then, okay, now we've said this, as Florine told you in a math framework, these things have two components. There's a space, like what is my object? And then there's the question of what is my metric? So how do I talk about what's a cheap or expensive deformation of my object? And sort of in this scenario, I want to build on something that's called elasticity-based metrics. Because, if you talk about deformations and talk about deformations of shapes or like shells or like surfaces, then I think, in Eurographics, it's easy to say, okay, I want to do something like elasticity, like my object should be an elastic object. And why do we want to do this also in the shape space context? Because it's a natural way to say, okay, for example, for this curve example here, like the left deformation from the top curve to the bottom curve is somewhat more natural and cheaper than having this like wobbly thing on the right side, which of course is, like takes a lot more elastic energy to do all these bendings. And to formalize this is, okay, we will talk about elastic shell energy that will have two components. So it tells you, okay, I have two realizations of my surface, x and x tilde. And then we basically, the cost of going from one to the other is given by two components, a membrane energy, which is tangential stretching. It's basically just how my singular triangles are warped. And then there's a bending energy that describes, bending as the name says, so how the curvature of my object is changing. We'll see a bit more in detail how this looks on the discrete object in a second. And then we apply something that's called Rayleigh's paradigm. And it's sort of a central thing that for these kind of elasticity-based metrics was introduced by like Rod Rayleigh in like 1900 something. And basically says that, okay, the cost of a small deformation is just the heat is lost due to internal fraction. So basically I make a tiny deformation and then I relax and everything that makes this a new reference configuration, and so the energy I have to spend on this because my object warms up my elastic object, and that's just described by this like local deformation. And basically how this translates into math is saying, okay, my metric now on my tangent vectors is just the Hessian of my elastic energy at rest configuration. Right, so you see over here, you say, okay, y is equal to x. So it's basically, I look at the elastic energy at rest configuration, I look at the Hessian, so that's positive definite. So it gives you a valid scalar product. And then this gives you the metric. And basically this is like saying like, okay, locally I have like linearized elasticity, right? So if you know about elasticity, if you want to linearize elasticity, make everything more simple in your life, then you do just that. You take a nonlinear thing, you apply the Hessian, and you get like a local model for deformations. And it's basically just saying, okay, that basically we built a local model of deformations on our shape space to sort of match elasticity. And that's basically the central ingredient here. And maybe to make this a bit more concrete on shells is to go back to these discrete surfaces that now sort of describe like a thin object. Basically you say, okay, it's like a thin object that has some with delta, and then you have this membrane and this bending component. And the membrane energy really just looks at your triangle-wise metric of your triangle mesh, so basically the derivative of your immersion squared. And then you look at how this changes between these two different immersions that you have, x and x tilde. So it's basically just a relation between them, the relative change. And then you apply some energy density on this per triangle, add some integration weights, so the area of the triangle, and sum this up over your whole surface. Very enough, and then, okay, the energy density can look very easy, but it can also look quite complicated in the beginning, but actually it's like very easy to read, so you care about changing of length, changing of volume, and you don't want your volume to go to 0. That's sort of the single thing. And then you have some weights that give you some material parameters, and so on. And then for the bending energy, what you do is, okay, you look at 2 neighboring triangles, then you have a dihedral angle between the 2, or between the normals of these 2, whatever you want to do. And then you just look at sort of the quadratic change of this quadratic difference between these 2 angles in your deformed and undeformed configuration. You add some integration weights, like of the area, associated with the edge, the length of the edge, so that makes sense that if you sum everything up, everything has a sort of a good relation to each other, so that depending how big the triangles, it makes all sense. And then you have a discrete bending energy. And you can see this actually, if you work with triangle meshes, these are things that are very easy to implement. I mean, it looks maybe a bit complicated, but you can do this in a few lines of code, and then you can have an energy that you can then plug into a shape space framework to get all these kind of things afterwards. And that's about discrete shells. And then, you can use this. I forgot this slide. You can, for example, here you see some geodesics that are computed with this. So you have this elephant, 2 gray elephants at given one. And you first compute interpolation, so a geodesic between them, and you get this, like a nice movement curving up of the trunk, and then you can continue this by the exponential map by shooting, and basically the deformation naturally continues, right? And to note, there's like no notion of what's an elephant in this model. It's just based on elasticity, and sort of these physical plausible deformations get out naturally. Same for the skeleton fingers. You can also do like deformation transfers for parallel transport, where you have these two faces. One that's smiling, and then one that's more like looking disgusting, and you can transfer and you get like happy, disgusting face, whatever that is, kind of for motion. And then finally, we can also do something like more elaborate. You can start to build like really like compute averages. You can try to compute like statistical model on this and try to do like low-dimensional things to get like low-dimensional deformation models of like plausible deformations. If you want to have more notion of what's a good shape than just being a shell. Oh, sorry. And then Florine will take over with the next fun space.
So we already saw in the beginning the space of closed curves as like a motivation to look at this. And now here, so we consider the shape space where each points correspond to a closed curve. And now this curve can be represented continuously by a function from S1 to some RD. So for example, just R2. So S1 as the circle as a parameterization, and then you get the shapes. So now, if you want to build a shape space out of this, the first question that you have is, do you want to include all curves, or do you want to maybe only include very regular ones, or do you have some specific other ideas in mind? So what you can basically consider is, okay, I only want very smooth curves, so those that are infinitely often differentiable, or so the lower space are less regular curves, so only the ones that have m derivatives. So now, I mean, you can make a choice here, and then the question is, okay, now the shape space, again, we want to ignore rigid body motions, but in this setting, we maybe also want to ignore reparameterizations of the object, because if you have 2 curves, and now you reparameterize the curves, then actually the shape of the curve doesn't change. So you probably also want to identify those. And now the question is, okay, if I want to build now my shape space, what metric can I choose such that it gives a meaningful metric and it also ignores these reparameterizations? And maybe one first idea that you would have is, okay, why not take just the usual L2 metric? So in this case, the metric just is defined by integrating over S1, so over your curve, the scalar product of your motion directions. So here this ds refers to arc length integration, which already has this parameterization of the curve inside. So actually, if you reparameterize the curve, the metric would stay the same. And then the path energy, you can just plug it in. So now you have an integral over time, which is integrating over the path. And inside you have the metric, which is integrating over your considered shape at this time point. So now, if you look at those two circles, you maybe now want to compute an energy that actually, a path that actually minimizes the energy between those two circles. And what happens is that you get a path that looks kind of like this, which is probably not what you would like. And actually you can show that if you now would even increase more of this, so add more of the spikes, the energy would further decrease. So you can construct paths now that have arbitrarily small distance with respect to this metric, which then leads to the follow-up that now the infimum of the energy of paths between those two shapes is actually getting to 0. And now you maybe wonder, okay, I mean, this is probably not a useful choice. So what can I do about this? And the basic idea is that the L2 metric is not introducing much regularization of your path. So actually deforming a normal direction of your path is kind of cheap. And what you can do is maybe a usual technique that you also do if you solve some other optimization problems. If you have the feeling that they are not well defined or your results are not regular enough, you usually add higher order terms. And this is the same here. So what you do is instead of only considering the L2 metric, you also add higher derivatives. So here the metric for m equals to 0, it would be the L2 metric before, but now you also include higher derivatives. And now you see that if you go up to 2, so now you now have an L2 part, you have the first derivative and the second derivative, and you sum them up, then you actually get nice looking interpolations. So here again, the purple shapes, between the purple shapes, this is a computed interpolation path, and the yellow is an extrapolation. And you also see here that you can play around with this weighting parameters in front of the metric terms, and you get different looking interpolation, and in applications this would be a design choice. So depending on what you would like to model, you could choose your weights in a way that they refer to the behavior that you would like. So the takeaway of this example is that sometimes you have to be careful because not every metric that you could think of or that you want to take is actually appropriate for your space. And especially on this Sobolev spaces of curves or also on surfaces, there's a lot of really mathematical theoretic groundwork that works on when do geodesics exist, when do they have regular solutions. And I personally like this article here by Bauer-Brouwels and Micho, because it's a really good starting point if you want to look closer into this, which is like an accessible information about like why use this metrics and what is the problem if you use other metrics and what results are there. So then the third example is the space of diffeomorphisms, which are just smooth invertible maps. And the reason why you want to look at them is that you are actually interested in images, which might seem at first a bit counterintuitive, but what you think of is that you have an image which is defined on some image domain in R2, and UA is the gray valued intensity function that gives you pixel-wise information of your image. And then you can also think about having another image B, and now on this image you also have an intensity function UB. But now instead of using this function UB, you could also think of deforming your domain and then applying the old transformation. So this phi here would somehow deform your image domain such that then you can represent UB by this concatenation. So here, the shape space, if you define it as the set of diffeomorphisms, then a path in the space actually corresponds, so a path now on this manifold is a path that at every time point gives you such a diffeomorphism. And now, so this is a try to visualize this. So at time point t equals to 0, you have some image, and at time point equal to 1, you actually get the final image UD by applying the diffeomorphism phi 1, so the one at the endpoint of your path, and the old intensity function. And now to define a metric on this space, you somehow want to measure, okay, now this diffeomorphisms over time, how much deformation are they actually causing? So how much is happening to come from image UA to image UD? And for this, you consider the Eulerian velocity. So this is just telling you at each time point exactly where the pixel is moving. And you take a similar metric there. So you now, similar to the Sobolev case, you just take a weighted sum over derivatives of your metric. So you have the L2 term, and then you have first and second derivatives. And this gives you now a metric to measure for a pass on this diffeomorphism, how much transformation are they actually causing. But now you maybe wonder, okay, now I have this diffeomorphism space, but actually I'm interested in images, so what do I actually want to do? And the usual application is actually if you have MRI images, you often have a template image that gives you like the basic outline of how your image actually should look like. So you can define a manifold where you fix this template image and then apply it to all your diffeomorphisms, and this gives you then a set of images. And now, to define a distance now between two images, you are not defining something pixel-wise, so you're not telling, okay, I measure the difference between pixels of my image UA and UB, but instead I go back to this diffeomorphism space, and there I measure how large is the deformation between image UA and image UB. And you measure this by measuring the difference between an identity, which should probably have distance 0 in your image space, and the diffeomorphism phi b. So what you actually do is you minimize the path energy over all paths in your diffeomorphism space that go from the identity to your final diffeomorphism phi b. And now we already showed you examples and talked about what shape spaces you can consider, but the question is, okay, now I want really to start to compute stuff. How do I do this?
Yes, and so to look at this, the central object, to go back to the math part now, was the geodesic ODE, right? We talk about geodesics, and there was the second order ODE that said, okay, how does a geodesic look? What is a geodesic solution of this? And so the core objective, if we talk about computational methods, is we have to discretize this ODE in time somehow. We also have to do it in space, because, for example, I don't work on continuous surface, but I work on triangle meshes. But we sort of assume this part as solved for now, right? We have triangle meshes, and we assume our triangle mesh, as I said, is a space of discrete shells, is the kind of object we're working on. So really we talk about discretization in time. So instead of having this continuous path, we want to have like this, discrete path of like individual steps going from one shape to another. And then we will look at the following at two sort of approaches to do this. There's like two different schools, I would say. One is what I call forward time discretization, or LDDMM style methods, or LDDMM is a method, it's been around for a while and especially popular in France. And then the second one is variation time discretization, which is more the school that we are from, which is like a bit newer approach, and they both have like advantages and disadvantages. We see this in a second, but as I think like the two major things we talk about. But for both of them, the shared goal is what you want to have in the first step is a discretized Riemannian logarithm, so interpolating geodesics, and a discretized Riemannian exponential, so shooting geodesics from an initial direction. And then afterwards you will see that if you have these two things, you can build many more algorithms with these two operations, but first you need a logarithm and an exponential. That's always the first step. So let's look at forward time discretization. And forward time discretization begins by looking at the exponential map. So you assume you have a point, you have a direction that you want to go in, and I just see, okay, there's an error. The gamma dot should, of course, be a v, some vector. So you want to shoot a geodesic in a direction. As Florine told you, basically what you have to do is you have to solve the geodesic ODE as an initial value problem here, right? So you say, okay, my covariant derivative, the second derivative of my curve is 0 along the curve in the notion that we talked about. And at point 0, it starts at a point, and at time 0, we have a direction given. And then we want to solve this ODE from time equals t 0 to time equals 1, and then this is my solution for exponential map. Okay, now the idea of forward time discretization is like very, very easy. Okay, saying, okay, now this is an ODE. So what do I do numerically? I apply some ODE solver that I know about to this ODE, and then I get a solution. So then I get something like this. It looks just okay. I have a discrete solution of my ODE. The first thing is just the first point I gave into it. Then at time equals 1, after k steps, let's say, I'm at approximately step 1, and I say, okay, this is my discrete exponential map. Easy as that. Well, not quite as easy, because you just saw that actually this covariant derivative looks like a second derivative. So if you're in a Euclidean space, okay, that's easy. But in a Euclidean space, your curve is just straight, so maybe not so interesting. But so you have to know what is actually the second order ODE, and how do I put it into my ODE solver. And that's sort of the question that you get to. And sort of the prime example of this is that you actually look at an open submanifold of Rn, or R3, which basically what this means is we don't have a curved surface as we looked at before, but actually we look at like a volume more, right? So if you're in R3, and but you have a different metric on this volume. For example, here you see this cube is warped a bit, so it's not like your typical Euclidean metric, but you have a different metric, but you're still working on the entire Euclidean space. And then what you can actually show is that you can write this second order ODE as a system of two first order ODEs. So you have this Hamiltonian system, where the Hamiltonian is basically operates on something that's called momentum. This is pi vectors, and it's basically just the inverse of your metric, right? Because as you saw before, basically it's a scalar product in the tangential space. The tangential space is a finite dimensional vector space. So you can just write it as a matrix, and you can talk about the inverse of this kind of thing once you've picked the basis. And then this Hamiltonian is just basically the inverse of this metric. And then your second order, but this metric, of course, depends on your point in space. That's important to note. And then basically your curve is just given by differentiating this Hamiltonian for the first component, and for the momentum, which is something like the tangent vector, the direction, you get basically the second component with the minus. And then, okay, in your initial conditions, so the initial point is still the first point that we start with, and your initial momentum, so the initial pi, is just multiplying your vector, your tangent vector you start with the metric at the initial point. So it's basically talking about, if you talk about physics, momentum is if you add mass to your velocity, and that's basically the same thing. You're basically saying, okay, I multiply with g. My metric is saying, okay, which kind of mass does this tangential vector carry in a certain sense, and this is your initial momentum. And then with this ODE, you can just do like very simple things like a forward Euler discretization. So you just, at each point you compute sort of the time derivative explicitly, and then you just go like a tiny step in this direction, which you can do because you're talking on an open submanifold. So we just have changed the metric, but we're still working on the whole space. And then you get this like computational directives that you can just follow that look very easy in the beginning, but sort of and then you basically start this, you do this once, you do it again, you get a new point, you get a new direction, and again, and at some point you're at the final thing that you want to arrive at. And basically this is also the case where this example where you mostly employ like this forward time discretization, which is, for example, the space we talked about, the diffeomorphisms has exactly the structure in the end. If you discretize it, there's like an open submanifold with just a different metric. But one thing I want you to note, you have to be able to do two things here. First, you have to be able to invert the metric, right? So this is a matrix. Maybe it's not super big, but it could be super big. So you have to invert the matrix. Or you just have to know by definition of your metric what the inverse is. Then you can do this. And also you have to be able to differentiate this inverse of the metric with respect to the point in space. So this puts like huge constraints on the metric they can use for this kind of approach. And actually for this like space diffeomorphism, this is true because basically they start with this and then they build a metric that makes this possible, and this metric still works well. But this is a huge constraint on your work. And then, so as I said, we want remaining exponential and logarithm. So far we have an exponential. Okay, we did some ODE time stepping just for this ODE with a bit of like clever things on like looking at the space that we are at. But now we need the logarithm. And the idea here is again very simple. Okay, say, okay, remember, the logarithm is the inverse of the exponential. So if we want to compute a logarithm, our job is, given some 2 points, P and Q, we want to find a tangent vector at my initial point P that the discrete exponential gives me this point Q. So that's the thing we do, and because it's the inverse, and then this would be the logarithm, or discrete logarithm, let's say. And actually what they do in this forward time discretization thing is like a very classical trick from inverse problems. You just formalize it as an optimization problem. Say okay, I look at all possible things I could do. I look at all possible tangent vectors I could take. I look at where they go on my space, and then I try to find the one that's close or closest to my point Q, the result. And then you choose some D, it's called data attachment term typically in this literature. It's something that measures difference between 2 points. This could be like just an L2 norm if it's like images, if you apply it to images. It could be something like the distance between vertex positions, if you apply this to like meshes or something. But you need to choose something that tells basically you're close. And so how does this look? Yeah, it's very easy. Okay, I start with some initial tangent vector V. I look where my exponential map goes. Okay, I see, yeah, it's a bit off by this amount of D. Then I compute the gradient, I pick a new one, and I repeat this until I'm like hopefully close, and I say, okay, this V now is my discrete logarithm. And so what's done algorithmically is, so there's a minimization problem. You apply your favorite first order minimization algorithm, like gradient descent or BFGS. And then the hard part you actually have to do is you have to differentiate the exponential map. But remember, the exponential map is just an ODE solver, so it's like time stepping, right? So it's like a very easy algorithm to follow. Previously, people just had to compute this by hand and do like chain rule by hand. Nowadays, you just implement everything in PyTorch or whatever and do auto differentiation, and it's actually not that hard to compute the gradient anymore. So that's also what these people do, and that's why I do first order optimization, because then you get first order gradients and not second order gradients. So to recap, this first approach is, so we get a discrete exponential map by applying ODE time stepping to the geodesic ADE, and this is actually typically very, very cheap, because as I said, you have seen this like simple algorithm I did for this open submanifold kind of thing. If your inverse of your metric is cheap, then you can do this in like milliseconds. But obtaining this discrete logarithm was by the inverse problem. So I look how far I'm off, and I optimize this until I found something that's close. And that can be like very expensive, because you have to do this many iterations to get to something that's good enough, unless you pick like a very good instantiation, of course. So algorithmically, it's a standard ODE solver for the logarithm. I actually didn't tell you much about this, but typically what people do in practice is they take a ODE library that works with PyTorch, and they just put in this ODE. That's actually what happens. There's nothing magic to it. There's no, you can, the ODE, as I showed you, forward Euler is good enough mostly. You can be a bit more clever, but it's not really something that's a lot of work. And then for the other thing, you need to do first optimization with autodiff of your ODE solver for the exponential. So like algorithmically, this is also like very easy, and once you have the metric and so on, it's easy to put on top to implement. And so if the typical shape space is that what I told you before is the space of diffeomorphism as it's applied to images and volumetric data, because actually the metric there is built that they actually write down the co-metric instead of the metric. So co-metric is the inverse of the metric, so they can do this kind of things. So now I want to talk about the variational time discretization, which is sort of our school, I would say, that we have been trained in, and it's basically the idea is to do the other way around. So before we did first the exponential, and then we did a Riemannian logarithm based on this. And here you do it the other way around. We first start with the logarithm, and then we look at the exponential. And so what we do is, before we looked at the initial value problem. So I have a point, I have a direction, and I want to shoot in that direction by solving this ODE in this direction. Initial value problem. But now we look at the boundary value problem for the same ODE. So saying I want to find a geodesic that connects 2 points P and Q. So this is the first problem I want to solve. Basically, if you look at the ODE, saying, okay, I have this ODE, and instead of like saying time 0 is this, and derivative of time 0 is this, we say time 0, the point at time 0 is P, and the point at time 1 is Q. And then we know from before that actually the derivative of this logarithm in time at the point 0 is exactly, of this curve is exactly the logarithm. So basically, by finding the curve, you can compute the logarithm. And okay, so the first goal is discretize this boundary value problem. How do we do this? And this is now sort of the key thing that we do here. Is, okay, remember, we go back. We know that computing this geodesic is minimizing this path energy thing. So you have, okay, all possible curves we could have on our manifold. At time 0, we had P. At time 1, we had Q. And then we have this path energy, right, which is basically something like the norm of our acceleration velocity, norm of velocity. And then the first thing that you do is you start to break down your path energy, because I'm going to have discrete steps in my energy. So I look at sort of what's the cost per discrete step. And I just, say, I introduce k middle points here at like uniform time steps. And then do sort of what we've done before with this estimation between like length and path energy. I do it sort of in reverse. So I apply the same Cauchy-Schwarz inequality. I get a lower bound by this term, and I actually see, okay, this is actually lower bounded by the distance. And so this is saying that, okay, my path energy is lower bounded by the squared distance between the consecutive points on my curve. And actually, as we learned before, both of these inequalities turn to an equality if my curve is a geodesic. So for a geodesic, it's actually the same thing, because our geodesic is also locally length minimizing, right? So okay, we say here now that we can break down our path energy into like locally looking at the distance between 2 points. And this is exactly how we sort of define a discrete path energy if I have just points and no continuous curve. Okay, saying, okay, I have k consecutive steps, and so if the cost, the whole path energy is just the consecutive summed squared distance between these points. But now actually I haven't done anything because there's still like a distance in there, and to compute a distance I would need to compute a geodesic between these 2 points in our continuous framework. So what we need now is something like a local approximation of square distance between 2 points on my space. And this is somewhat similar to a metric, as you'll see. Okay, so here's what we need sort of in a theoretical thing. So we need a W, we call it now. And now we see, oh, we've had a W before, maybe this is an elastic energy. We'll see. So it's a square distance between these 2 points, and then there's some error terms of higher order. So, you know, if you don't know O notation, just saying, okay, it has to be a square distance up to a certain quality of approximation. So the very first thing you could do, like the very first basic approximation distance is if you have 2 points on a like embedded manifold in R3 or Rn, you can just take the difference between these 2 points in ambient space and plug them into your Riemannian metric, even though this is not a tangent vector. Like the Riemannian metrics defined on the whole space anyway, you can just do this and have like a local squared distance between these 2 points that locally matches your metric. Then, as I said before we had this discrete shells example, and there we applied Rayleigh's paradigm. And Rayleigh's paradigm was like, okay, we're saying basically my metric is my second derivative of my elastic energy locally, my Hessian. And this means if you do it in reverse, you can actually show that now your elastic energy has turned into a local approximation of distance on your manifold around a certain point. And this is exactly one we could use now on this framework as a local approximation of distance. And you could say, okay, like the elastic energy is also easy to compute. You can actually implement this and have a squared distance on your space of discrete shells. And then for this example of Solev curve, this is maybe at first a bit more involved. What you do here is you do like a candidate curve, which just do like you have 2 curves, and just interpolate linearly between these 2 curves. And then you look at the path energy of this like linear interpolation. And then actually, because this is all like, you know, in this Sobolev norms, you can actually compute this by hand or with also some numerical differentiation if you want to, but you can compute by hand what the cost is of this linear interpolation, and you can take this as a local distance approximation, sort of as a candidate curve. And if you look close enough, then it's a good approximation. Okay, now we want to actually compute discrete geodesics, and I want to give you some also understanding what this is, because now we've replaced really the squared distance by this like approximation. So here, if you apply this framework, typically what you do is instead of really defining a metric, you define a W that tells you like a local distance approximation between 2 points, and then you can apply this whole framework. And basically then a discrete geodesic is a discrete path that minimizes this discrete path energy for a given fixed endpoints, and so basically just sum like consecutively this like W between 2 points and follow. And then there's this K which actually popped out of this like Cauchy-Schwarz inequality before, but it's just also like if you refine in time, if you more and more time step, that this is consistent and converges to something in the end. And what happens, how can you imagine this? Now on my space, basically, like square distance, if you know Hooke's law, is also something like the energy that's stored in a spring. So basically, you can imagine now for this sort of problem as, or it's proportional to, there's some factors. What you can now imagine is, okay, if I do this problem, I have discrete points on my manifold, and I put springs between them. And now I can like move this path, but I want to find a sort of the relaxed version of my path where all the springs have least stored energy. And so for example, for this, okay, the springs are like quite extended and quite big, especially the first one, and then I start to relax, and maybe get to something like this. But still we see that we have these springs on the lower left, like one is still very much extended, and the other one is like very tiny, so we start to relax them further. And then in the end we have something like this, where all the springs are like as relaxed as possible to connect the 2 endpoints, and they all have the same length. which goes back to what Florine told you about like this constant speed property. You automatically also get this in this discrete world here with this energy, that all your points have like in the end, if you converged, have like same squared distance to each other. So you have like a smooth, also discrete thing. And what do you do here is you have to, algorithmically, you have to implement this, and you have to implement your W, and you have to implement, of course, your shape representation, and then you can write down this energy, and you need to compute derivatives, and then you also apply basically off-the-shelf minimization methods. Typically, we do like second-order things because we can compute second-order derivatives of this elastic energy. This helps you a lot. But you could also just use autodiff on this energy, do BFGS, and get to something. There's also people that do that, and it works decently well. So there's not, again, sort of the whole like interesting thing here is really in the modeling, and then the optimization for these kind of things is not so interesting. Sort of the inverse now, the exponential map is a bit more involved here. What we want to do is we want to build this as the exact inverse of the speed logarithm. And sort of the key observation that we make to do this is that every subpath of the discrete geodesic is also a discrete geodesic itself between these two given endpoints. Because basically, if we just with Euler length, because we just take the same path energy, we have the same W's there, is the minimizer is one part and it's all of all parts. And what this also means is that I can build my my geodesics recursively, meaning that okay, once I know how to go one step from my starting point, I can do another step because this has to be the same geodesic than the first geodesic, and I can continue this step by step to get the end. And then you get this complex, this complicated notation. It's just saying, okay, if I do a k-step geodesic from my first 2 time points. One difference here a bit is that in this variation times gradations, typically we talk about not tangent vectors, but the first 2 points in a geodesic as initial points. We can also just do a linear interpolation between the first 2, for example, to get the relation between tangent vectors and points. And this is the same as okay doing like going like k minus 1 steps, and then continuing this geodesic by looking at the previous one k minus 2 steps by just 1 step more. So basically what you do is, okay, in images, you have first one, then another one, then another one, then another one, and you arrive in the end. But, okay, so I still have to tell you how to do the first step. That's the crucial one, because once I know how to do the first step, I can do all the other steps just the same. So really what we care about is like 3-point geodesics. So you have 1 point, I have another point, how to find a third point such that this thing is a geodesic. So before we said, okay, geodesics are minimizers of the path energy. So here we have the path energy for like 3 points, which is just the summation of this like approximation, this W, first and a second point, and then a second and a third point, or 0 and 1 and 1 and 2. And then, okay, what does it mean to minimize this? You can look at sort of the first derivative, you compute it, and use for the middle shape, because the first 2 end shapes are first fixed. And you see that, okay, my geodesic, my 3-point geodesic has to fulfill this equation, which is just the first order optimality criterion. And then, okay, now assume that we have x0 and x1 given. We want to find the x2 such that this thing actually becomes 0. So for given x1, x0 and x1, we want to find the root of this equation, because then this thing fulfills the geodesic equation, is the minimizer of this path energy, and I'm fine. So, okay, then I do this, and I have a root finding problem now, so I apply Newton's method, or any other thing, but really Newton's method. I find the root, and then this root is the first step of my interpolation. So I apply this, I done this, and then I take basically x1, x2, do the same thing again, take it x3, and so on. So basically the thing is really you break this down to like a 3-point problem, and then you do it consecutively, and then the way you do it, you find out that actually the thing in the end exactly minimizes the discrete path energy. So it's exactly discrete geodesic. It's actually the inverse of the discrete thing. There's like no data detachment term or something in this way. We have a few theoretical results in this that I quickly want to go through, which are kind of nice. So it tells you that there's work from like our PhD advisor Martin Rumpf and a former PhD student Benedikt Wirth on this kind of framework. They tell you that discrete geodesics exist and are locally unique. So if you have a convergence, that if you make finite paths, then your minimizers converge, the energies converge, and you have some convergence property. If you manifold fulfill certain assumptions, but for fine dimensions, you're good. And then, this is like nice because you get this more continuous paths. And then also what I told you before, that these paths have like eco-distributed energy along, which means there's no jumps in your paths that you get out of it. And now to recap, like the variational time discretization is, we start with a discrete logarithm by minimizing this discrete path energy. We had the discrete exponential recursively by doing like each step is a root finding problem. And before I said, okay, the one thing is cheap, the other thing is expensive. Here, both things are relatively expensive. So the first thing is you have to really minimize this path energy. And this is really like a minimization problem that if you do on like a lot of shapes at once. And the second exponential, you do it recursively, so each step is not expensive, but still it's a root finding problem. So it's not as easy ODE time stepping as before, but they exactly fit together. And have some other examples. Okay, I told you, you do optimization or you do Newton root finding for these two problems. And then typical spaces for this are space of immersions, space of measures, like discrete shell things that we talked before, discrete curves that we talked before. And we will see more examples later on. And now, actually, I want to, as I said, okay, we have exponential logarithm, you can do more, and once you have these, and Florine will tell you what you can do more.
Yeah, so this is just meant as a quick overview, what actually you can now do once you are able to compute exponential and logarithm. And we already talked about the geodesic average, so you saw this two examples there. So what you want to do now, you have samples given you, so you have given shapes, and you would now want to define an average shape. And actually, the average is now defined as in the Euclidean setting. So there, the average is just the minimizer that minimizes the distance to all your points, which in Euclidean setting is just summing up your coordinates and computing the mean. However, now in this shape space setting, there's no closed form solution for this minimizer. So what you do is you can do an iterative algorithm where you pick an initial guess Z0, then you compute the logarithms, so the directions to all your shapes. So these are the green arrows here. And then you sum up those directions, which you can actually do because they are now in the tangent space. So you are linear, so you can just sum up. And then you get a yellow arrow out. And this tells you, okay, in this direction I have to move to arrive at my actual mean. And now to again have a point on your manifold, that is the next iterate, you compute an exponential direction, exponential step in this direction, which gives you point Z1. And then you can iterate this process until you reach, it kind of converge, which means that your vectors actually sum up to 0 and you don't make large progress anymore. And then maybe also another tool that you know from Euclidean statistic is the PCA, which is just a way to find a low-dimensional approximation. So again, you have shapes, and you now want to kind of find a subspace that can approximate those. So you start by computing the geodesic average, just as before. Then you can also compute the logarithms, or you already have them, to your shapes. And now the idea is to just compute an Euclidean, so the usual PCA in this tangent space using your logarithms. So for the third step, what you actually do is you solve this squared problem where you solve for the functions u, which are the PCA components. And the only difference here to your usual PCA is that you actually have to take the norm into account. So you have here the Frobenius norm with respect to your metric, and you also want that your modes are orthonormal with respect to your Riemannian metric. So here, this is an example where we computed PGA modes in this discrete shell space, which basically show you that this modes give you kind of like the main motion directions of your shape. And this then allows you to maybe define a submanifold that is now only spanned by those modes. So if you want to not work in the whole shape space, but just in some subspace, you can use this. And then this is just to show you that also you're maybe familiar with linear regression, where you have data points and you want to fit a linear curve in between. But what you can also do is actually fit a geodesic in between. And this is usually done this application here is from a medical application where they have time points, so they have some part of the brain, I think it's the thalamus, and they have it at different time points, and then they want to fit a smooth interpolation curve that fits to those time points. So now the question is, we saw discretized versions, and do you have to implement all by yourself, or what existing stuff is out there?
Yes, so I will talk briefly about sort of existing software frameworks, and but I can sort of give you the hint first. There is some, but the situation is not great right now, I would say, in this kind of space. But first off, what should be the scope of like a framework that we talk about? So if you want to do shape spaces, you need a few things that you actually need to have. First, you have to have some kind of shape representations, right? You have triangles, meshes, images, point cloud, whatever you want to work with. Typically, these will be given to you, right? So if, for example, you want to work triangle meshes, you can use, I don't know, like Open Mesh, Geometry Central, whatever you want to. So you pick some framework and you're good. There's tons out there. And then you have to represent your metric on your shape space somehow. So either you have to implement this metric tensor, this G that we talked about, we have to implement this like local distance approximation, like this W that we talked about, or there's other ways to define metrics by, for example, having transformation of your space. And then if you actually want to be a shape space framework, I would say you need to have at least two things. You need to implementation of the Riemannian logarithm, so you need to be able to compute interpolating geodesics, and you need to be able to have a Riemannian exponential, so you need to be able to shoot geodesics. And then once you have these, it would be nice if you have additional algorithms like averaging, parallel transport, the PGA, and geodesic regression. But I think the first three things are the really things you should have if you want to call yourself a shape space frameworks. And here are some examples going by like from dead to alive, more or less. And so the first thing is a thing that's super popular and is still in some regions is the diffeometrica. And they really focus on this like forward time discretization I told you about for diffeomorphisms, like really for these image applications. I've already showed you for these brain things with diffeomorphisms. It's a Python framework built on PyTorch. It has just the space of diffeomorphisms. It has basically all the algorithms. But the big problem is it's not actively developed anymore. So the development stopped at some point. It was like a lab at INRIA Paris, which has been working on this, but then they changed focus a bit, and now it's sort of dead in the water, and this used to be like the go-to framework for a long time. So this is sort of something that I want to caution you about, like look at if these things are still active and still being developed, because this thing is still being used a lot by like practitioners, but no one's developing it anymore, and if you go on their GitLab page, it's just overflowing with issues of like PyTorch version problems and so on. Then there's the framework that I've been working on like all the time I've been doing my PhD and postdoc. And really the focus here is a C++ framework, which is a bit unorthodox by now. But still, it's a space of discrete shells. You really work with triangle meshes. You have this elastic energy I told you about before, and there's also some other variational problems. You have all the basic algorithms. You have the exponential map. You have averages, PGA. And then really there is some, like, even though it's C++, I want to tell you there's like a nice interface that you can do things with. But as I told you in the beginning of the talk, I'm currently not in academia, so currently active development is no, just not happening. If you like it, I mean, it's open source, you can work with it. I think the code is decent, but not great. But maybe if you take your favorite LLM, it's easy to use. Then there's a morphometrics framework. It's from a group in Berlin, and what they really focus on is shape processing with differential coordinates. So maybe if you work on like discrete surfaces, differential coordinates representing your mesh not by vertex positions, but by different notions like the length of your edges and dihedral angles or some like first derivatives. And this is really what they focus on, because then you can do a lot of things like almost like linearly. And they also basically have the whole gamut of algorithms that you would like to have for this. And this is still actively developed. It's in Python, but it has like this very narrow focus on differential coordinates because that's the thing they're interested in, because they apply this to like medical shape analysis. Then there's scikit shapes, which is something like a new kid on the block from the people in Paris, because they were traumatized that diffeometrica is gone, so they introduced scikit shapes, especially Jean Fedi, also in INRIA Paris, and it's really what their focus is. They want to bring all these shape space tools, but they want to build a framework that is like nice to use for, let's say, biologists or whatever, right? So that they can apply this to problems that they have in real life. Right now they focus on diffeomorphisms, but they also have this elastic energy I showed you before implemented, because I was in Paris for a while and told them about them. They thought it fun to implement it, and they did. But as you can see, it's still like the very early days of development. They have a few things now. They have some interpolation geodesics, but they don't really have shooting perfectly yet. They have some pre-processing, which has been a big focus for them, because to work in practice you need good data. And one thing really, what they focus really on like people that apply this. And so they, for example, the language, they don't say like logarithm, they say registration. I have two shapes and I want to register them, right? That's sort of the thing that I think from the application problem and not from the sort of underlying algorithm. And then the big player that there is Geomstats from INRIA Nice and UC Santa Barbara. And so they want to build like a broad framework for statistics and geometric data based on this kind of shape space framework. This is like still very much active in development. It's in Python, but you can use PyTorch, you can use NumPy, whatever. They have different backends. They have all kinds of spaces implemented. Like they have classically like spaces of matrices, which may be also interesting for shapes, but you have curves, surfaces, landmarks, probability distributions. They have basically like abstract frameworks so that you can, once you have a space and a metric implement, you can implement all the algorithms like exponential logarithm easily on top. Yes, and it's, they have all kinds of different things. So it's a huge framework. It's still in active development. It's very nice for some things, but the problem is because it's so general, for like each specific problem, it's not the best, right? Because it's not super performant, for example, for these kind of curves and surfaces applications, because it's not optimized for this deeply at all points. And it's maybe sometimes a bit complicated, but I think this is the best thing that we have right now. And, if you want to just start playing around, this is like a very first good step, and there's a lot of things you can do with it, and a lot of great things, and just that it has active development and people working on it is a big plus in this scenario right now. Because I told you, like, a lot of these things are not actively developed, and I wouldn't say there's like this one framework that does everything. Maybe that's not so important anymore. As I said, there's LLMs. You can maybe vibe code one quickly. I don't know. I've never tried. I would know, but but still, the situation is not perfect. There's some interesting things on there, but if you start working on this, maybe this is the first step. But maybe you could quickly also start rolling your own things. But I would, encourage you to maybe try to give back by open sourcing things. And with that, we get to the shameless advertising part I promised in the beginning by some recent works. And Florine will begin by talking about snakes.
Yeah, so I guess we repeatedly said that we want to consider shape spaces and we don't care about rigid body motions and we ignore them totally. But actually now we shift perspective and include them because we want to be able to compute really motion paths where you get this snake wandering around. And for this, you of course need a position in space and you need a rigid body motion. So far we have a way to compute nice shape deformations in shape space, but actually we are maybe interested in how to move from A to B, so answering a question like how can the snake be the fastest at the end point and lose not much energy when doing it. So now instead of considering the shape space, we consider kind of a total space of configurations where we also include all positionings of the snakes. So instead of fixing the snake, it's now allowed to move everywhere. And I just want to mention here that it fits kind of in a very similar framework. So again, we minimize an energy, and this energy measures the cost for the snake to deform, but it also measures the interaction with the environment. And now we solve for a minimizer of this energy not in the shape space, but in this large total space. And the secret here is hidden in a constraint, which is kind of a motion constraint, which I'm not going to explain in detail, but it's basically describing the fact that the snake can only deform its body. It can't just jump in space. The only control it has is to deform its body. And then this body deformation actually leads to some forward motion. So this constraint is actually saying how does a shape deformation lead to a motion? And then with this you can compute actually this crawling snake. And you can also answer questions like how can you optimal turn? So now if you want to say, okay, this should now make a 90-degree rotation, in shape space, it wouldn't be possible because this curve and the one which is 90-degree rotated actually is the same space. But here now you get actually a turning snake. So Josua will go on.
Yes, and I talk about the problem that I'm showing now because so far I talked about this elastic energy and I told you it gives you like nice geodesics, and here you see one of these nice geodesics that's like very plausible. Well, maybe not so much. Actually, it looks like very painful human motion, so you wouldn't want to do this. And so the question that was here that we had in this problem is how can we actually change our shape space, where shape space is space of discrete shells, to obtain self-avoiding surfaces to avoid not actually have embeddings and not just immersions. So this was a project we did with Keenan Crane, with Henrik Schumacher, my PhD, Martin Rumpf, and me, because I just realized I forgot to put the citation. And the idea is what we wanted to do here is, maybe Keenan's work on repulsive surfaces and so on, we use this repulsive energies that he's been working on, where repulsive energy is basically just an energy on your surface that explodes if your surface gets close to self-intersection. We wanted to, and the specific implementation that we use is this tangent point energy that Keenan and Henrik have been working on with Caleb and so on. But basically just what you do is you have 2 points, you look at the radius that is tangent to one point and intersects another point, and like the inverse, the reciprocal of this radius, if you integrate this with your surface, explodes exactly once you get close to self-intersection. There's a lot of nice things you can just do with this energy. If you look at the paper from them, actually quite old by now. It's 5 years already. God damn it! But it's a nice energy. You can do fun things, and we wanted to implement this into the shape space. So what we did is we included this into our discrete path energy by now having this elastic part, this W in the beginning, and then we have the change of this energy afterwards. And it turns out that if you do this, exactly what you get is you sort of can avoid these intersections. For example, here's the geodesic I showed you before as a video, this green one. We have the intersections, and then if you take this modified path energy, where I indicate this another energy, you basically get an interpolation that avoids the human body and looks a lot more natural. And you can do other fun things with it. You can talk about simplified tedious work, so you can look at inverting your clothes, turning them right side out after doing your laundry. And all these nice renderings are due to Keenan, so I have to give credit for that. And you can solve age-old problems like how can a camel walk through the eye of a needle? So by making it very, very tiny, compressing it, but no self-intersections, and then you go out again and you turn it back into a camel. So yes, age-old questions, maybe a valid answer, you have to decide. And but I want to finish off with some open problems that I think still exist out there that you could work on if you like. So I have one first problem that someone we ignored a bit, which is mostly a problem for like these discrete shells problem things. It's a problem of shaped correspondences. So all these things you need to I told you about, so if they need to know if you have two shapes, how do they correspond, which point corresponds to which point. So for discrete shells, had these things, but there's two approaches to do this. So the first one is what I told you about, this forward time discretization. You use a data attachment term that basically takes care of this somehow. So you have the difference between two shapes that somehow is invariant to these kind of correspondence problems, and this is typical for this diffeomorphism type world because they just warp them onto each other and you can maybe directly compare them. Or you can do what we did in the last years is just ignore it. That's the thing that you do for discrete shells, but they say I have a fixed triangle mesh and I only care about realization of this fixed triangle mesh. Then I can just look at difference between works positions and I'm fine. But there's two problems. The first one is for these like data attachment terms, typically the quality of the results is limited, especially on fine details. You get like overall shapes, you get they are good. For example, that's nice for if you have like shapes in your brain, like the hippocampus or thalamus or whatever. This is good enough, but if you have, for example, a human, and you have like tiny fingers, then maybe you get the hand right, maybe you get the hand right, but not the fingers, no way, because there's just a too small detail to measure in these terms. And for the second issue, well, it's kind of very limited in things you can do in applicability because you have to have one fixed triangle mesh for everything, and it is limited in robustness because once your mesh is crap, everything goes to hell. That's how it is with meshes. And the idea that I think is nice, there's a lot of work on, and recently in shape correspondences and geometry processing. This is a nice paper from the group in Aachen. Mark has been doing some very interesting things at this year's SIGGRAPH, I think. And I think these kind of advanced now that have been done in like intersurface maps recently would like pair very, very well with shape space methods and could now maybe build a method that's high quality and robust at the same time. Would be great. And the other thing I want to tell you is shape space methods are often slow actually, because you have to optimize a collection of shapes and so on, and these kind of things are very complicated. There's different approaches. You do multi-resolution methods. You can do like reduced order methods by trying to build lower dimensional approximations, or for discrete surfaces, you can work in differential coordinates, what I told you about. Thing is, none of these are general, easy to use and give high quality results, so it's always like a very specific thing you have to do per problem. maybe you can come something up that works on a general basis, based on PGA or whatever. I'm not really sure what the best way to go here is, but this is a big thing. Yeah, we can solve on this. Great. And the one thing is like something that's really not a problem, but more of an idea that I have, or that we had. That's sort of the thing that right now, like many generative models that you have out there in machine learning they'll sort of look at low-dimensional representations, right? We don't really know them perfectly, but they have some notion, it seems in there, it's like low-dimensional. And actually, if you can capitalize this by using some shape space frameworks, I think you could do very interesting things. And just like one example is like score-based diffusion models. They use the score function. If you know, then you know. And basically, the score function is the gradient of the probability density of a distribution. So you have a data distribution, and you try to learn the score function, so it's gradient of its log probability. And actually, what turns out that is intuitively, this is a vector field that points to the direction of steepest increase in data likelihood. So you go to likely data. And if actually your data is on a low-dimensional manifold, and it turns out your distribution is sort of like a Gaussian around your manifold, it turns out the score basically is essentially a projection onto your manifold. Because you go the direction, steepest direction to data likelihood, like the data's likely is on your manifold, so basically you land on your manifold. And in general, you can sort of get something like denoising operator and projection. So what I want to say here is that basically these kind of like diffusion models, they learn some geometry representation of data space somehow. And there has been some works now, for example, at this year's ICLR, and there's like a lot of coming out in this direction that try to like understand this and try to use this in like Riemannian frameworks and so on. I think this is very interesting because this would like generalize shape spaces a lot. And so if you want to do more like machine learning things, but still think this kind of geometric data is interesting, maybe this is a way to go. And with that, we come to the end of our course. So to summarize, we learned about shape spaces today, which we model as Riemannian manifolds in mathematical terms to like be able to interpolate between data averages and do general processing and collections of geometric objects. The first two basic operations that we talked about and seen is that if you want to interpolate between two shapes, you can do it geodesic on the space. If you can extrapolate, you could look at the exponential map. Then you can start to build more elaborate things based on this, like do the averaging, do statistical analysis once you have these algorithms to really do statistical analysis on geometric data. And finally, we've shown you some, like, we call it shameless advertising, or I call it shameless advertising, not Florine words, and to show how you can use like interesting, fun things with this. And I've shown you some problems, how you could maybe move on from here. And with that, we thank you for your attention, and of course, you're open to questions. So are there any questions in the room? Yes, over there. Please wait for my sorry.
Yeah, thanks. There you go.
Thank you. So thanks for the very interesting lesson. You've talked a lot about optimizing over the space of immersions, and then at the end you said there was recent work on the self-intersections with this like repulsive energy. Have you thought about optimizing over like the space of embeddings or something instead?
Okay, so essentially, yes. So basically the self-intersection thing is basically moving from a space of immersions to a space of embeddings. I didn't really use these terms, but yes, then once you can guarantee the intersection free, you have embeddings, and then this is the space of embeddings.
Okay, makes sense.
And you can actually show that with this distance I introduced, basically once you move towards an immersion that's not embedding to a self-intersection, like the distance goes to infinity, so you actually avoid it.
Okay, so it does change the space.
Yes. Anyone else so early morning?
My question is about the part where you were talking about the correspondences. The problem of optimizing for the deformations in correspondence seem to be like related. So I was wondering if there are any works who do that jointly and try and either penalize bad correspondences and deformations from each other.
Yes, it's a bit of a yes. So basically, in this like forward time disgregation world I told you about, there's like this data attachment term, and basically they always treat like finding correspondences and finding a geodesic as the same problem more or less. So you have two shapes, let's say two images, and you find a deformation that warps them onto another, and then you have some metric on images that tells you if images are closed somehow, or if it's a three-dimensional space, if they align somehow to ambient space, and then you can derive correspondences from this. But the problem is, what I wanted to say there is that basically, if you compute the energies in these correspondences in this framework at the same time, usually the quality of results is not as good as it is for like specific correspondence algorithms as we've been using Eurographics, right? So sort of reintegrating these two like smoothly into a pipeline that does everything, then again at once, but builds on all these advances would be a cool thing to do.
Thank you.
I'm curious for the work for the slithering snake stuff. If you found different metrics you chose would relate closer to how actual snakes move, if you could use how actual snakes move to almost like learn metrics or anything like that.
Yeah, so we have one example where we actually took like from a biology lab some like movie of a real snake. And we try to like compute if we choose like the weights of our metric that we kind of approximate the movement. And I guess, so of course we don't fit it 100%. And I would say for like how easy we actually chose our metric, so it's a very simple metric which has not very much biology included, we actually approximate it quite well. But of course, if you really want to like go into detail with this, you would have to model like really that the snake has maybe a thicker head and a smaller tail and so on, which you can also include in the model. But yeah, at some point it gets complicated. But of course, if you want like, then you can just like make the metric more biology dependent, and I guess then you can also use it for biological application. But we stayed like on a bit more abstract setting with this.
Related to the question that he asked previously, would there be a way to learn the metric? Like, in terms of if you have data, then you learn the metric, and then, I don't know, like an inverse problem?
I mean, I guess there is. So, I mean, if you consider general works about metric learning, or then you can afterwards apply this metric in the shape space. I guess it always depends on how good your data is, how much samples you have, and if you have some idea about what you want to model. But yeah. Yeah, so we are also around, at least I'm around until the end of the conference, so you can just approach if you have further questions.
Thank you.